The last bit of our proof is to look at using inequalities and graphs, and we've seen that idea already in a couple of things. I'll start with something like this. And by the way, I'm not suggesting you would use a graph to do this, but it's an example of using a graph to solve one of these pronumeral in the denominator questions. So we could draw a graph. Now, x squared divided by x plus 2, I've drawn in there x squared and x plus 2 to try and get an idea of what this graph looks like. So I'm going to split it up in a boundary so I know where it's positive and negative. I know there's a vertical asymptote at -2. On the left-hand side of that, I'm going to have a positive number divided by a negative number. So I know it's negative, then I'll go positive and positive. I'll work out the oblique asymptote. We can do a polynomial division. X minus 2. So there's the oblique asymptote. It ends up looking something like that. Now, we're saying when is that curve below the horizontal line 1? So we could read off the graph and we've got the answer. The downside of this is it requires an accurate graph. I got lucky here because the solutions are nice integer solutions, 2 and -1. But if they're not, then a graph's going to be a bit hard to do it on. So our final answer for this one then would be, well, it's below at x is less than -2 and also in between -1 and 2. So as I say, it's an example of using a graph to solve a problem, an inequality problem. Again, I'm not suggesting that that's the best way to do this question. Let's look at more interesting ones though. Whoa, that is getting old. 1990 HSC. It's the y equals square root graph there, and they've plotted in a few points for us and drawn in the outer rectangles. First thing we had to do was show that this graph is continually increasing. Well, we know it's increasing when the derivative is greater than 0. Again, remember, write those things down because you're presenting a solution for someone else. It's not for your benefit, it's for someone else's benefit. They want to understand why you're doing what you're doing. So the derivative is 1 on 2 root x. Well, that's always going to be positive whenever x is greater than 0. So we know it is increasing for x is greater than 0. Maybe I got a little bit paranoid because it did say x is greater than or equal to 0. And obviously that derivative doesn't have a solution when x is equal to 0. So I decided to actually have a look at the point 0, 0. I know when x is greater than 0, y is greater than 0. So it's starting at the origin. But as soon as it goes past the origin, it gets bigger. And then we know it's continually increasing after that. So yes, it is increasing for x is greater than or equal to 0. Quite possibly you didn't have to do that last bit. Maybe I was just being paranoid about 0. Hence show. Now the clue, of course, is in the diagram that they gave us. There it is. And as it's increasing, all of those outer rectangles are obviously going to have an area that's bigger than the area under the curve. So that's the idea I'm going to use. So therefore, I've got that expression. That's exactly what it is. I just have to work out what the integral is now to confirm it's 2/3 n root n. So let's integrate that, and we'll end up with 2/3 x root x, sub in n, sub in 0, and we get the result they want, 2/3 n root n. Now they want us to do an induction to prove the other half. So now that all of those things are less than or equal to this expression. Okay, let's do our induction. First case, n equals 1. Left-hand side's 1. Right-hand side is 7 on 6. And yep, 1 is less than 7 on 6. So it works for the first case. My assumption will be root 1 up to root k is less than or equal to 4k plus 3 on 6 root k. We now want to prove true for k plus 1. Again, I'm moving everything to the left-hand side, and I'm going to try and show this expression is always negative. Okay, well, it's a series type, so I'll split the series up by putting in the second last term. So what I've done is I've grouped the root k plus 1 with the 4k plus 7 on 6 root k plus 1. We've ended up with minus 4k plus 1 on 6 root k plus 1. That's left me with my assumption, which I can now substitute in and say, well, this must be less than or equal to this lovely expression there. Okay, well, let's put it all over 6. We now need to play around with the numerator to try and get what we're after. I want to pull the surd together, if I can. because I think what we're trying to prove had some multiple of root k plus 1, didn't it? So I want to try and get them, both terms having root k plus 1. So the first one then, if I make it all inside the third, it'll become 4k plus 3 squared times k, which is 16k cubed plus 24k squared plus 9k. Remember, I'm trying to get k plus 1 there, so I'll divide that by k plus 1. And I get 16k squared plus 8k plus 1, but I got this remainder of minus 1. However, we're playing with an inequation here, not an equation. So I can get rid of that minus 1, because this line here clearly has to be less than the line underneath, because it's the same thing except minus 1. So it has to be less than that line. Now I can pull out the root k plus 1 that I wanted in common over here. In fact, is that a perfect square? 16k squared plus 8k plus 1? I think it is. I think it's 4. It is. It's 4k plus 1 all squared. Look what we end up with. 0. Excellent. We've proven what we want. We were trying to show that is all less than or equal to 0. We have our results. So therefore, it's true for k plus 1. If it is also true for k, since it's true for 1, etc., etc. Okay, so the next part of the question, little question, can we just estimate what root 1 plus root 2 up to root 10,000 is? Well, what we've now done is trapped that expression between two values. All I've got to do now is sub in n equals 10,000. If I sub in n equals 10,000, there is our expression. So let's calculate out the two n bits, and to the nearest 100, they actually turn out to be the same. So if I am trapping this expression between 666,700 and 666,700, it's fair enough to conclude that that must be 666,700 to the nearest 100. Let's try this one. We're going to prove x is always bigger than sine x for x is greater than 0. And I'm going to draw a graph. There's y equals x. There's y equals sine x. Now, it's not good enough to just say, oh, look at that. The blue is always above the red. Fantastic, we've done it. We've actually got to prove it. Now, they obviously meet at the origin. So function x equals x. The derivative is 1. So I know that line has a slope of 1. Now the trig graph. This is where you have to bear with me, because I know we haven't looked at differentiating trig yet. So trust me when I say when you differentiate sine, you get cosine. All right? So whenever in between 0 and pi on 2, I'm just looking at the first quadrant. Cos x will be less than 1. So the slope of the sine graph must be less than 1. But the slope of the line there is 1. Well, if it's going up with a slope of 1, but the red one is always going up with a slope that's less than 1, it must always stay underneath the line. So y equals x will increase faster than y equals sine x. So we know x is greater than sine x in the first quadrant. Now after that, well, sine x is always less than or equal to 1. And y equals x just keeps going up and up and up. So clearly, x has got to be greater than sine x. Thus, it's always true that x is greater than sine x, for x is greater than 0. I think that shall do us.